start?
Down.
Gotcha.
I hit
Oh,
it.
you already did, okay.
We're going. I will begin with a word of prayer. Him. Dear Father, we thank you for this day. I thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. So as you guys have probably noticed, I have posted video to make up for our lost Monday. So you should watch those sometime soon, right? Now, basically what I say in those videos is just the rest of chapter 2. That doesn't really hurt not to have seen that as you see this, all right? So I'm going to go on, talk about systems of equations. You know, your homework, which is due Wednesday, you know, problems 11 through 18 are all on systems of equations, but they're all relatively simple questions, all right? Shouldn't really take you that long to do them. So here we go. What is a system of equations? So we're talking about systems of linear equations over R equal to, we'll focus on the case of a field. So being that we're working on equations over a field, that means that we can divide, all right? The story of how to solve equations over something that's not a field, like over a ring that possibly has 0 divisors, it's a little bit trickier, all right? So I'll leave that for somewhere else. I might have given you a token homework problem to explore it, but that's probably about as far as it goes. All right, so here's the deal. We have something like a11 x1 plus a12 x2 plus a1n xn equals to b1. a21 x1, a22 x2, a2n xn equals to b2, and so forth. Each one of these is an equation, all right? It's an equation with coefficients. So here the a's are taken from the field. The x's are unknowns at the moment. And let me just emphasize what's going on here. We're looking at m equations in n unknowns. The n unknowns, I'm using the notation x1, x2, dot, 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 xn here at the moment, right? The goal is to figure out what values we can stick into x1 through xn such that we solve not 1, not 2, but all m of these equations all at once. We're looking for a simultaneous solution to all m of these equations. Now, we've talked a little bit about matrices and column vectors and so forth, and so one of the things we can immediately do is to recast this system in terms of a coefficient matrix, a vector of unknowns, and a so-called inhomogeneous term. All right, so this can be rewritten as the matrix a11, a12, dot, 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 a1n, a21, a22, dot, 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 a2n, and so forth and so on, down until we get to am1, am2, all the way over here to amn. All right, this is the so-called coefficient matrix. The coefficient matrix. We're really looking at that times x1, x2, dot, 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 xn. If you look at this m by n coefficient matrix, right, times that n by 1 vector of variables, what do you get? You get a m by 1 column vector, right? That m by 1 column vector is exactly the right-hand side of the above equations. So the column vector here we're looking at is b1, b2, dot, 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 bm. So this is the so-called inhomogeneous term.
Why is it called
Uh-huh. Well, so my point, let's see here. So if we think of this equation collectively as star, then what we've rewritten it as AX equals to B, right? Where the m by n matrix, I'm just calling this whole m by n box of numbers A. I'm calling the vector of variables X, right? X. And the inhomogeneous term is B. B is an m by 1 matrix. So to answer your question, why is it called inhomogeneous? Definition: if B is equal to 0, then star is a homogeneous system. So thus, if inhomogeneous, meaning if that is non-zero, it's not homogeneous. Further terminology, if there exists a solution to this system of equations, then it's said to be a consistent system. If there exists x naught in Fn such that a x naught equals to b, then ax equals to b is a consistent system of linear equations. So my question for you, before we get into any, we're gonna look at specific gory examples today. All right, don't mistake this abstraction for. This is not where we're going to stay today. All right, we just need to set the table. This is the terminology. But before we get to, the things that you guys will like more, my question to you at the moment is a homogeneous system consistent? In other words, can you solve AX equals to 0? Can you tell me, is there a solution to this system? X naught equals to what? 0, right. So, yes, set x naught equals to 0, then a times 0 equals to 0, right? Therefore, x naught equals to 0 serves as solution to star. So homogeneous systems are really nice in the sense that they're always consistent. You can always find a solution to a homogeneous system. An inhomogeneous system, on the other hand, who knows? You may or may not be able to find a solution to an inhomogeneous system. All right? Let's look at some examples. So I'll do 3 examples here. Example 1, I'll do x plus y equals to 1 and x minus y equals to 1. Example 2, I'll do x plus y equals to 0 and then 3x plus 3y equals to 0. And then finally, example 3 will be x plus y equals to 0 and x plus y equals to 1. I'm looking at these examples all over the real numbers, okay? So let's keeping it real. I will not apologize for this. So how would you solve 2 equations and 2 unknowns? Oh, add or subtract the equations? I like that. So what would happen if we add these equations? What do we get? 2x equals to 2, therefore x equals to 1. And then y is equal to 1 minus x, which is equal to 1 minus 1, which is equal to 0. Therefore, it looks like the solution is 1, 0. is solution. How about example 2? Divide them. How about what if I just take the second equation and divide by 3? What do you get? So, I mean, this is a homogeneous system, right? It's got a solution. In fact, it's embarrassing. It's got infinitely many solutions. So the solution here, we just put y equals to minus x for any x. So here, the solution set is equal to, let's say, x comma minus x, such that x is real. What's the solution set in case 1? It's not a simpleton, it's a, what's a set containing just one element? Yeah, singleton. Oh. But it's also kind of stupid, but there it is. I mean, okay. You're like, well, isn't that the same? Well, no, the solution is a vector. The solution set is a set. These are different objects, yes? All right. So if I ask you to find the solution set and you give me a solution, what am I going to do? I'm going to take away your points. That's what's going to happen. But I don't want to. Like, again, by the end of the semester, I have far too many points. I'd really like you to keep them, you know? So, and how about this one? How about we just substitute equation 1 into equation 2 or vice versa, right? Substituting gives us what? Yeah, 1 equals to 0, which is, yeah. So what's that mean? Can 1 be 0? No, so there's no solution. So this case, the solution set is the empty set. Yeah. Is this a homogeneous system? It better not be, right? And it's not, is it? What does the system look like in matrix form? It looks like this: 1, 1, 1, 1, x, y equal to 0, 1. So as you can see, the inhomogeneous term, 0, 1, is non-zero. This is not a homogeneous system, okay? Can you guys tell me another way to think about these three systems? Lines, yes. So we can think about these graphically. So what's the first system? It's really y is equal to 1 minus x. Y is equal to 1 plus x, right? So we have y-intercepts of 1 and either slope minus 1 or slope 1. They cross at 1, 0, which is the solution that we found. That's the one place where both equations are true, and that is the unique solution to two lines intersecting, as long as they don't have equal like skew lines, right? Different slopes. Case number 2, graphically, we can think about as well. What is that? What's going on with equation 2? What am I looking at? I'm looking at y equals minus x 2 times, right? So that's just this equation and this graph, and then that graph again. So arbitrary points on this line are on this line, and the points have the form x minus x. Any choice of x works. The solution set's infinite. This you don't see so much in earlier courses, right? So often we look at systems where there's a unique solution, right? But one of the things you guys got to start to think about is solution sets could be infinite. Or if we're working over a finite field, you might just have a finite number. Now this one, what's going on here? We're looking at y equals minus x and y equals to, 1 minus x. So what you're looking at here is parallel lines. Both with slope minus 1, they never intersect, right? So there's no common point for both equations being simultaneously solved. And if we're looking at real equations and more unknowns, Actually, these three cases are it. There's either a unique solution, there's an infinite solution set, or there's no solution at all. These three cases continue to be the truth if we're working over the reals. If we're working over a finite field, it's a little more nuanced than that. There's either a unique solution, a solution which has the number of things in the finite field to a power, or there's no solution. So, all right, so you guys did some stuff. We divided the equation by 3, right? We added or subtracted equations. We looked at substituting one equation to another, you know. These are things we manipulated a given system of equations to solve it, right? So the question is, how do you want to solve a system in general? And that is where row operations come into play. So there are 3 elementary row operations, which I will write down here. And I will show you how we can use these 3 elementary row operations to solve systems of equations. So here's type 1. Type 1 row operation, we interchange row I and row j. Here I is not equal to j, all right? What's the, so this is, so what I'm describing now is row operations on, oh curses, I have, sorry guys, let me just go ahead here. We can swap rows I and j, type 2. We can multiply both sides, multiply row I by c not equal to 0. Type 3. Type 3, we can multiply both, we can add c times row I to row j, where c is any scalar. All right. I think I need to give you, let me illustrate what I'm trying to say in an example next to that, if you don't mind. I don't think I've made myself clear yet. I'm sorry, guys. So, you know, if I had, suppose I was looking at the equation x plus y equals to 2 and x minus 3y equals to 7, all right? So the thing I haven't told you guys yet is we introduced yet another matrix called the augmented coefficient matrix, all right? So I want to try to show you where that's coming from. I'll get to that in just a second, but the idea here is this is equation 1, this is equation 2. The first thing, and it's kind of a stupid thing, but it's the thing we can do, is to go, no, you're wrong. This is the first equation, and that is the second equation. All right? So the augmented coefficient matrix for this system is the following. It is 1, 1, 1 minus 3. We put a bar here, and we put 2 and 7. So what you're looking at in the black above the blue is just a shorthand for the system where we're not writing the variables. But it's understood that the coefficient matrix is to the left of the vertical line, and then the inhomogeneous term is to the right of the vertical line in the augmented coefficient matrix. And so the nomenclature here is row 1 swap with row 2. That's a row operation on the augmented coefficient matrix, and all it does is like this: 1 minus 3, 7, and 1, 1, 2. So, of course, can you see that what's above the blue in the black? That is the augmented coefficient matrix for the swapped system. Let me put it into words. The row operation on the augmented coefficient matrix achieves the same thing as doing the corresponding operation to the equations themselves. So if I flip the equations, it's the same as flipping the rows in the augmented coefficient matrix. All right? Here's another one. If I had x plus y plus 2z equals to 7, and minus x plus y minus 3z equals to 2, all right? That's a system of 2 equations and 3 unknowns, right? I could do what? I could add them, that's true, but I'm on type 2 right now, so I'm not going to do that. You're right, though. That would be a good thing to do towards the purpose of actually solving this problem. I agree, totally agree. But what I'm going to do is something stupider, which is I'm just going to say, you know, I could multiply the second equation by 2. I could take, I say 2 row 2, like that. Well, I could just multiply the second, I shouldn't say 2 or 2. I can multiply by 2, right, times 2, so to speak. And that would give me, oh, why am I, good grief. So the first equation, just leave it. It's minding its own business, doing nobody no harm. Second equation, multiply by 2, I get minus 2x plus 2y minus 6z equals to 4. I mean, that's kind of a stupid move because it doesn't really help us solve it or anything, but it's something you could do. Would that change the allowed solutions to this problem? No, I mean, it's the same equation, right? You multiply an equation by a non-zero number, it's not changing the solution set's the larger point. So what this looks like for the augmented coefficient matrix, which I'll do in red this time, is, and mostly I'm doing this to introduce notation, guys. So we got 1, 1, 2, 7, minus 1, 1, minus 3, 2. That's the augmented coefficient matrix for that system. All right? Yep.
Could you flip the rows? Could you have 2 different rows with augmented coefficient matrices?
We could do many things, yes. So this is 2 row 2. Let me answer your question in just a second here. So 2 row 2, we get 1, 1, 2, 7. So that what this means is I multiply row 2 by 2. So I got minus 2, 2, minus 6, 4. And of course, if you look at the equation that we got above by multiplying the second equation by 2, well, what's in red below it is, in fact, the augmented coefficient matrix for this system. What's the advantage of working with augmented coefficient matrices is we're not writing down x, y, z, x, y, z, right? And after about the 30th variable you write, this gets to be a major labor-saving notation. All right? And it starts to take on a life of its own as we go on. Now, what you're asking is, could I then flip the rows? Sure. I could do row 1 flips with row 2 here, and that would leave me minus 2, 2, minus 6, 4, and 1, 1, 2, 7. I mean, yeah, we could do that. Sure. And then type 3, which is, you know, adding a copy of one equation, one row to another, that corresponds to like adding or subtracting equations, right? Adding equations would be like putting c equal to 1. Subtracting the equations would be putting c equal to minus 1. So let's see here. X plus y plus z equals to 2. X minus y minus z equals to 4, right? And maybe I would like to do what? Like add equation 1 to equation 2. That would give the first, well, equation 1 is unaltered, right? Equation 1's minding its own business. Equation 2, on the other hand, becomes what? 2x equals to 6. Because the y and the z cancel. Now, the way that looks for the augmented coefficient matrix is we're going from 1, 1, 1, 2, 1, minus 1, minus 1, 4, And then what do? We do row 2 goes to row, oh, I'm sorry, I've forgotten my own notation. So the way I denote that is row 2 plus row 1. This is a kind of sneaky notation. Whichever one I write first is the one that's being modified. The one exception to this is row swap, in which case 2 rows are modified, right? Like 1 and 2 are both swapped. So, but 2 row 2, that means I'm messing with row 2. Row 2 plus row 1 means I'm messing with row 2. If I wrote row 1 plus row 2, that would mean I'm adding equation row 2 to row 1. So whichever one I write first is the one being modified. That's the notation I've been using. So row 1 is unmodified, and row 2 is giving me 2, 0, 0, and 6. Hey, while we're at it, if we do, let me call this thing M. All right, so take M and take 1/2 row 2. What do you get? Right? I get to that matrix. Then how about I swap rows? Or what do you want me to do here? How about I subtract? Let's do this. Let's subtract row 2 minus row 1. What's that going to give us? 1, 1, 1, 2. Yeah, 0 minus 1 minus 1, 1. And then, going from there, curses. What if I do row 1 plus row 2? If I do add row 2 to row 1, right, then it will cancel this 1 and 1 and leave me 0, 0. 2 plus 1 is 3. 1 plus 0 is still 1. And then one more move. Yeah, multiply row 2 by minus 1. And that will give me this. The reason I'm doing all this is just to introduce a result. So the thing I just wrote down has a special name. But before I even tell you that name, can you tell me what makes that last thing very special? What does it tell you? So what did we do? We added the equation. We multiplied by a number. I don't guess we didn't switch the order of the equations this time, right? But everything we did it change the solution set? It did not, right? I mean, the point is multiplying by a non-zero number or adding an equation to another. It doesn't change the solution set. The solution set is invariant under this process. So if we can solve the equations which correspond to the final matrix, it's the same as solving the equation which corresponds to the original matrix. What are the equations which correspond to the final matrix? X equals 3 and y plus z equals to minus 1. Therefore, y is equal to minus z minus 1. So x equals 3, well, that's easy enough to understand. You can't mess that up, right? And so y equals to minus z minus 1 suggests that, y plus z equals, so what we do is we use z as a quote-unquote parameter in the solution. So the solution set, in this case, would be 3 minus 1 minus z, and then z again. Let me instead of using, let me use it easier to see z, such that z is what? Well, it's not clear, but I'm keeping it real still. So assuming that we're talking about a real equation system. I mean, this could just as well have been a rational system of equations, right? I didn't really say where the system of equations was living. Where's its home? But there you go, that's the solution set. So geometrically, what's going on here, guys, is if you've taken Calculus 3, you might recognize this is a plane with normal 1, 1, 1. This is a plane with normal 1, minus 1, minus 1. And what we just found is the solution set. So what's going on here is you've got two planes, like one looks like this, and one, I can't draw it, looks like like that. Right? And then where they intersect, this is the solution set. It's where the equation for both planes are true. Geometrically, it's going to be the line which is perpendicular to both normals. So if you were to take the cross product of 1, 1, 1 and 1 minus 1 minus 1, you in fact would get 0 minus 1, 1, plus or minus up to a scalar, which is how some of you are solving that problem right now, which is fine. But we can also solve looking for places where two planes intersect by solving this system of equations. So what I just did here is called row reduction. But this is row reduction done in a very haphazard way, right? We were just kind of meandering, doing things, and I finally stumbled into this matrix here, right? This has a name. This kind of matrix is called the reduced row echelon form. This is the RREF of the, so this original matrix back here, my board is getting too cluttered. I'm sorry. This right here, though, was, curses. Dang it. This one right here is the AB. If it's okay if I'm going to erase. So this right here is the original system's augmented coefficient matrix. So we did row operations and out popped this. This end result is the so-called reduced row echelon form, or REF, of AB. Fun fact, the reduced row echelon form is unique, and you can always read off the solution set from the reduced row echelon form once you understand just a couple of basic rules. All right? So one of our main goals today is to start to understand the algorithm for finding the reduced row echelon form from a given matrix. Right? So yeah, each matrix corresponds to a system of equations, fair enough, but we start to stop thinking about the system of equations directly and just think about how to do row operations on a given matrix. We understand that if we have a matrix, it corresponds to a system, but we don't even have to look at the system and we can still do row reduction. Let me show you what I mean by that. I mean, you could tell me what the corresponding system was if you wanted to, and I do ask questions like that at times. Let's try one. So suppose we had 1, 2, 3, 4, 1, 4, 0, 0, and then 2, 2, 2, 2 there. I'll regret this, but anyway. So here's a matrix. I would like to show you how to find the reduced row echelon form of this matrix. So what we do is we begin by identifying the first pivot position. The first pivot position is going to be like you try to make it the upper left corner of the matrix, all right? If there's no 0 already there, you flip a row to make it non-zero if you can. Yep. Doesn't have to be, no. So this, and I'm just calling this matrix M, right? So that's my first pivot position, the upper spot. My point is, if you don't have something non-zero there, you want to do row swaps until you get something non-zero up there. If the first column is all zeros, then you can't put a pivot position in the first column. You go to the second column and you look for the first column where there's something non-zero, and you make that non-zero thing go to the top row. That's step one in the algorithm. So that's our first pivot position. The next thing we do is we do row operations to try to clear out below the pivot. We try to zero out the things below the pivot. So in this case, we're going to do row 2 minus row 1, and we're going to also do row 3 minus 2 times row 1. So that gives me 1, 2, 3, 4. Nothing changed there. And I got myself a 0, a 2, a minus 3, a minus 4, subtracting row 1 from row 2. And then I got myself a 0, a minus 2, looks like a minus 4, and what's 2 minus 8? Minus 6, all right. Great. So at this point, we have cleared everything out below pivot 1. We now move on to look for our second pivot position. So the next pivot position, you want to make them sort of like stair step down. This will be the next pivot position. All right. If you had 0 there, you do row swaps with the things below the second row to move them up there. If that's not possible, you go on to the next row. All right. The pivot columns after this is all done, they're always going to be like E1, E2, E3. We're not there yet, but just foreshadowing. So second pivot. Then the standard row reduction says clear out below the pivot. So what I'm going to do is row 3 plus row 2. So what do I got? I got myself a 1, 2, 3, 4. I've got myself a 0, 2, minus 3, minus 4, nothing changed there. But then adding row 2 to row 3, I've got 0, I've got 0, I've got, looks like a minus 7, minus 10. Guess what? We are done with pivot 2. We have cleared out below it. All right? What we're doing right now is the so-called forward pass. Now we go on. We look for the next row down, and if there's a row of zeros, then we're done. If there's not, we make the next thing down, the next the next pivot. This will be our third pivot. Yep.
What's the difference in reduced row echelon and just regular row echelon?
We'll get there. We're not there yet, but we'll get there. That is a good question for like 3 minutes from now. So now this, at this point, we're, so the row echelon form depends on what you're reading. Some people might already say that this is in row echelon form. Other people would insist that row echelon form has to have the following. So row 2 divided by 2, row 3 divided by minus 7. You get 1, 2, 3, 4, 0, 1, minus 3 halves, minus 2, oops, and 0, 0, 1, 10 sevenths, yeah? And so this is what your calculator might give you as the REF, the reduced echelon form, not row reduced. This is not unique. Depending on the order of things that you did, you could end up with different things here. So far, what I've done so far is the so-called forward pass. This completes the forward pass. So forward pass, we identify pivots and we sweep out below them. All right? Come on, stupid watch. It's so hard to give me a time. Oh, sometimes. Anyway, now the backwards pass, what we do is we go the other way, starting with the last pivot to the first, clearing out entries above. All right? And so, you know, to get rid of those two, what do? I do row 2 plus 3 halves, row 3, and I do And I'm also going to go ahead and do row 1 minus 1/3 row 3, right? Wait a minute. No.
Row 2.
3 row 3. 3 row 3. What's that?
For row 2 plus 3 halves, row 3.
Row 3, yeah. Oh, minus? I think we need plus because we want them to cancel.
Oh, yeah, you divided by minus.
Yeah. Right. So anyway, so we got 1, 2, 0. What? And then we have to think about it. What is 4 minus 3 times 10/7? What's 4 minus 37? Negative 2/7. Very good. 0, 1, 0. And what is minus 2 plus? So we need to do, I'll write it down here. We're trying to do minus 2 plus 3 halves times 10/7. That's what goes here. One seventh? All right. I'll allow it. I'm just kidding. I hope you're right. 0, 0, 1, 10/7. Congratulations. We just cleared out above the third position, third pivot. Now we need to clear out above the second pivot. So what's the finishing blow, if you will? Finish it. Let's see here. Sorry. Very violent. And what the first row didn't do anything. Just mind its own business. It didn't have it coming. So row 1 minus 2 row 2 ought to do it. And so that's going to give me a 1, a 0, a 0, a 0, a 1, a 0, a 0, a 0, a 1. Oop, I'm sorry. I seem to have invented a bar. So I think the 7th and the 10/7, they're just still minding their business over there. The real question is what happens to that minus 2/7? Minus 4/7. Right. And that, my friends, is the reduced row echelon form of M. Now, and what I did for you was more or less follow the Gaussian elimination, Gauss-Jordan elimination for this matrix. Gauss-Jordan elimination is this algorithm where we select pivots, make a forward pass, clear out below the pivots, and then make a backwards pass, clear out above the pivots. Once you're done, every pivot column should just have, see this is? This is E1, this is E2, this is E3, right? So you'll have pivot columns which are just the standard basis, and then whatever's left over from there. It doesn't have to go like that. There's like a lot of other flavor options. All right, yeah.
Where were the pivot positions once we started the backward pass? I got to where the third pivot position was the -7, the circling right there.
Where are the pivot positions? They're in the same spots. The pivot positions are still the same. It's just we're going backwards. So like, and honestly, when I do this, I'm not a slave to the Gauss-Jordan algorithm, to be honest with you. Like if I was doing this in the wild and I wasn't a slave to the algorithm, I tend to like to clear out above and below the pivots as I'm going. Like when I see this, it just screams at me, add row 2 to row 3 and subtract row 2 from row 1. See, because then I would have had 0, 2, 0 going forward. And I would never have had to do this last step. There's like a lot of variations on the theme, but if you follow the Gauss-Jordan algorithm, you'll always get to the reduced row echelon form. All right, so there's safety in the algorithm, but there's creative room for interpretation here too. And I don't, to me, it's not terribly important that you know the algorithm absolutely, by the book. It's that you're able to use the 3 row operations in concert to achieve the goal is what I'm mostly interested in. At times, I will ask you to use the specific Gauss-Jordan algorithm just for the sake of having, for the sake of specificity. Because if you use the Gauss-Jordan algorithm, then there's a specific sequence of operations that you would uniquely do. But anyway, listen, so what does that mean? Now, going back to, what was your name again? I should know your name.
Josh.
I know you. Josh. Well, I will, you can remain Josh for the YouTube, yes.
Just so I'm understanding, so when you're done with all of it, one of the rows is E1, one's E2, and one's E3?
It depends on the matrix, but the pivot columns will always be standard basis vectors. And what happens with the rest of the columns, it depends on the example. We'll see there's a lot of different cases.
Okay.
But this one, we could go back and think about this as a system, like Josh was wanting to think of this as a system, right? And so what would the difference be if we were thinking of this as a system? Just this, right? And we draw that and this. And what did we just learn? We learned that x plus 2y plus 3z equals to 4, and 1x plus 4y equals to 0, and 2x plus 2y plus 2z equals to 2 is equivalent to the system x equals to minus 4/7, y equals to 1/7, and z equals to 10/7. I don't know about you, but I much prefer to solve the system on the right, right? Like, someone tells you, solve this system of equations, you should be like, sure, I can do 10 like that. You know? This, on the other hand, thinking. Now, geometrically, what's going on here is this problem we can still visualize in 3 dimensions, right? So 3 equations, 3 unknowns. If you think about it in R3, that would be 3 different planes. And we're looking for where 3 different planes intersect, right? So you look at 2 of those intersecting, it gets you a line, as long as they're not parallel planes. And then you add a 3rd plane, and that's going to cut through that line. And it gives you just that one point, which is, well, the thing I just covered up. The thing I wanted to make sure I told you, because, okay, so you have some homework problems, right? Some of the homework problems are really, really kind of silly. Like problem 11, I give you 2 equations and 2 unknowns. I tell you, find a matrix A, which is the coefficient matrix, and a vector of variables V. Here, I'll tell you what the V is in part A. Like V in part A would be X, Y. Part B of problem 11, while we're waiting for this thing to warm up, I've got 2 equations in ABC. What's the vector of unknowns going to be there? V equals to CBA. I'm messing with you. It's ABC. Or it could be BAC. The point is, once you write down one, it forces you to write down a specific coefficient matrix. But there is a choice of ordering, isn't there? But a decent human being would make it ABC. You're like, stop. Stop. My point is, you got choices. Now, part C, I've got x1 through x5. We got 4 equations and 5 unknowns. So there, the vector variables V would be what? x1, x2, x3, x4, x5. I'm fighting myself not to make some kind of stupid comment about other ordering. All right, come on, wake up. Problem 13, you just need to write that down and look at it. 2 matrices are equal only if their components are equal, right? So you write down the equation in problem 13 and look at it. You should have 4 equations and 4 unknowns. You write down those equations, then you go back to this technique and solve it. All right? Problem 14 and 15, you need to plug in those points into the equation. For example, if I plug 1, 2, 2 into the equation, that gives me A plus 2B plus 2C equals to D. If I plug in the point 2, 3, 3 into the equation in problem 14, I would get 2A plus 3B plus 3C equals to D. I plug in the point into the equation, the 3rd point, 0, 0, 2. It gives me just 2C equals to D. You go back at what I just said, there were 3 equations in the 4 unknowns, A, B, C, D. That's a linear system. You can solve it. And then problem 16, 17, and 18, these are just straight up, just do the row reduction. right? So you need to get some practice on that. Now, you're not alone. There is wonderful software online. I sent you a link already. I want to show you this, and then we'll be done, if I can find it. Come on. So let's see if I made a mistake. How about that? So this is, there's a link in the announcement, right? Third thing down, transforming a matrix to reduce, so it's got row echelon too, see that? So reduced row echelon form. You click on that, and you pick the number of rows. We did 3 rows, we did 4 columns, right? What was my matrix? It was 1, 2, 3, 4. It goes row by row, which is kind of annoying. 1, I can't complain. 4, 0, yet I did, 0. 2, 2, 2, 2. And we submit. And bam. These are the steps in the Gauss-Jordan algorithm. There's your pivot. See what he does? Clears out under the 1, selects the 2, clears out under the second one, right? And so forth, and so forth. And then he does the backwards pass. And there it is. So you just need to follow this for problem 16, well, the last 3 problems in your homework. You're like, should I just copy this down? That's not the idea. The idea is that you're not alone. You can check your answer. This is something you need to get fast at before test 1. Row reduction is an important technique, okay? So I shut up. Anyway, see you guys Wednesday.